So today we're going to start a new part of the course. We're going off the textbook, but I'll recommend another textbook or text to read from if you want to. We're going to be talking about entanglement, reduced density matrices, and teleportation. And this is going to be a new postulate of quantum mechanics that deals with composite systems. And this is where a lot of the weirdness of quantum mechanics comes up. All right. So before I start, there's a new homework post that's posted. Please give me feedback. Is the homework useful for you guys? Does it help you follow the lectures? I can adjust as you wish. So the homework and all of that, the course is for you guys. All right. So a little bit of a personal story. This topic is very personal for me. When I was a high school student, I was really into astrophysics. And I used to go to the library in the university in my hometown. And one day I picked up that book, Werner Heisenberg's book. It's his memoir about early days of quantum mechanics, all the neat things that discovered and how fascinating it's been, early 20th century. And I remember thinking to myself, what's going to be the thing of our generation, right? We missed the quantum revolution. What's going to be our thing? Then in that library, I found this book, Quantum Computing and Quantum Information, which is what I recommend that you guys read from. So for this part of the course, I learned linear algebra from that textbook, actually. It's a very, very nice text. And the most interesting thing at the time for me was there was a discussion of quantum teleportation. And this is early days of internet. I look it up. Stanley Popescu and Anton Zeilinger had demonstrated experimentally teleportation in vacuum tube or some laboratory set up in vacuum and like for something that was like 30 centimeters or something. So fast forward a couple of years, I go to college, August 2004. The news comes out that Anton Zeilinger has achieved quantum teleportation over the Danube River. That's 600 meters, going from vacuum, 30 centimeters to 600 meters, right? That's when it really piqued my curiosity. I thought this is going to be the thing of our generation. We're going to live with quantum teleportation being a fact. This is August 2004. Fast forward 2007, just see the rate of it. Same group, Anton Zeilinger, they achieved teleportations in air at night, no vacuum, nothing, no laboratory conditions, in between two islands, two Canary Islands. This is at night in air, right? So this is 134 kilometers, not even 3 years later, right? Then go a little bit further, July 2017, a Chinese team achieved teleportation from the Earth to a satellite, right? So what we're going to be talking about in this part of the course is definitely experimentally, it's something that's exploding right now, and our generation is going to be using this weird quantum teleportation. All right, so of course, surely this name Anton Zeilinger stuck in my mind, but he was awarded the Nobel Prize along with 2 other people. And you can see that actually the description. They were awarded for experiments with entangled photons, establishing the violation of Bell's inequality and pioneering quantum information science. That's all about entanglement. So we'll talk about next lecture. It's going to be about Bell's inequalities. All right. So, good. So what are we talking about? Most of what we've talked about so far all of what we've talked about has been about single particle quantum mechanics. So we talked about a single photon, a single particle. We talked about the postulates of quantum mechanics, dynamics, the state description, right? And we talked about measurements. Those are the things that we discussed. At the time I mentioned, there is a postulate that's about composite systems. So far, the weirdness of quantum mechanics you've seen is the superposition, right? That's a novel phenomenon. which is all about, like I've heard about shorting the cat. Is it dead or alive? It's in superposition of it, right? And there are complex numbers that appeared. So that is weird. I cannot stress this enough. In going from single particles to quantum to multi-particles, this composite postulate is where the true weirdness comes up. And this is not superposition. Entanglement is a very, very bizarre phenomenon. So we'll see. I'll try to go through this in very basic examples. All right. So let's recall what our description has been so far. We've talked about single quantum particles. For example, we talked about the spin half atoms, the spin mode of silver atoms, which was either classically, it was either up or down. So a binary thing, 0 or 1, or but quantum mechanically, it could be in a superposition of it that we represented using a two-dimensional complex vector, right? Here, the state is described using a digit, a binary digit, 0 or 1. Here is described using how many variables? 3 real variables, 2 complex numbers with a unit norm condition that C12 plus C22 has to be equal to 1. Each of these are complex numbers, so 2 variables. 2 variable 4, this is one constraint, 3 real numbers, okay? And we described everything in the language of two-dimensional complex vector space. We also talked about a free particle where this becomes continuous, but for simplicity, and everything I say about composite systems applies to particles as well. But for simplicity, we're going to talk about spins. That's just because dimension 2 is easier than infinite. All right? Okay. So at first, hopefully by the end of the lecture, we get to quantum teleportation. Along the way, I'll make some mathematical definitions. You might have seen them or not. But as usual, this linear algebra, this mathematics is sort of forced upon us to explain the weird phenomenon we're seeing in nature. This is not someone who was obsessed with math and was just trying to push for this. This is the only and simplest description of what we observe in nature and experiments. All right? Okay, so let's start simple. How do we describe 2 spins? Classically, how do we describe 2 spins? If a single spin was a binary thing, classically, up or down, 2 spins would have 4 options. Up, 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 down, down, up, down, down. So if you just follow your nose and follow exactly what we've talked about, you would say that you would represent this system quantum mechanically with a 4-dimensional Hilbert space. A vector, which is which belongs to a 4-dimensional complex vector space called Hilbert space. Good? Everyone's with me? Already something insane has happened. Something totally, well, actually, more than one thing. There are many insane things that have happened just already at this point. One thing that this innocent-looking formula statement has dramatic consequences. Can anyone guess where are the consequences? When we talk about multiple particles, the dimensionality of the Hilbert space grows insanely fast. If I have 100 spins, I'm talking about the Hilbert space of dimension 2 to the power of 100. This is a vector space of dimension 2 to the power of 100. That is an enormous Hilbert space. Now, when I talk about a piece of, like, microscopic piece of material, it has an Avogadro number of particles, right? 2 to the power of Avogadro number of particles is an absurdly large number, right? So the Hilbert space in dimensionality is exploding really fast. So the state space of quantum systems is unimaginably large. And we will see that the vast majority of these states will have this weird entanglement phenomenon. All right? So everything is, are there any questions about this simple? Right. This is just like we're following our nose. And then you already see what happens. Good? All right. Let me, to be able to describe what I'm saying better, let me introduce a mathematical concept in vector spaces from linear algebra. It's called a tensor product. What is a tensor product? Let me just first motivate it. What I'm trying to do is I'm trying to come up with a mathematical model for how to construct the Hilbert space of a composite system. As you can see, if I have a Hilbert space of dimension 2 for particle 1, Hilbert space of dimension 2 for particle 2, when I put them together, the dimensionality of the Hilbert space is multiplied, right? So what I want is an operation that takes two-dimensional vectors or d-dimensional vectors and d-dimensional vectors and spits out a d-squared dimensional vector. Good? How would you do that? The most naive thought would be tensor product. What it is, actually, let me write it on the board and then we'll describe it. First of all, for two vectors, we're going to represent it using this notation. So if this is a d-dimensional vector, or d1 dimensional vector, this is a d2 dimensional vector. This is a vector that lives in a d1 times d2 dimensional Hilbert space, right? It satisfies the following properties. If you have a complex number, you could multiply it on the first vector, second vector, it doesn't matter. If you add two vectors, addition is distributive from the left and the right. But what is this operation? It's extremely intuitive. Here it is. If you have a vector of two numbers, another vector of two numbers, how are you going to construct a vector of four numbers? Or multiply them in all possible ways. First, C1, D1, C1, D2, C2, D1, C2, D2, right? So what I'm doing, let me draw it on the board. This might be helpful to think. Here's my first vector. So I'm going to call this vector psi, okay? This is C1, C2, da, da, da. First, I write C1, and just imagine what I'm doing is something like this. C1, first element, C1, second element, C1, third element, and so on and so forth. Then C2, that. C3, that. C4, that. Put all of these guys next to each other, and you get the tensor product, right? So let's just do a simple example. If you have up, which is 1, 0, tensor 1, 0, I have to multiply 1 by 1, that is 1. 1 by 0 is 0. 0 by 1 is 0. 0 by 0 is 0. The second one is this. 1, I just copy 0, 1 here. And 0, I just copy 0. 0, 1, 1, 0. 0, I copy 0. Because 0 multiplied by anything is 0. 1 by this is a copy of that here. Similar, oops, sorry. There's a typo here. Similarly, 0, 0, 1 is 0. 1, I just copy this guy down here. So now you end up with an expression like this, right? This is the very definition of tensor product of Hilbert spaces. It's the most naive thing you would guess, and this is the thing we're going to do. Are there any questions? There is another operation if you do to two vectors. If you take, there are actually only two operations you could do together. If you have the vector 1 dimension d1 and vector 2 dimension d2, you could construct a vector of dimension d1 plus d2 by sticking this down here, right? That is called direct sum. We'll come back to that later. This is not what we are doing. What we are doing is we want a vector of dimension d1 times d2, This is called tensor product, right? These two are the only two operations you could do to these vectors, and they both have analogs in quantum mechanics. For composite systems, we're going to be dealing with tensor products. Is the idea clear why we're doing tensor products? Because the number of options must multiply, right? Up, down, the four options. Up, down, up, down. This is the only thing we've got. Can anyone see already where things, already on this slide, you should be able to see something crazy has happened. This was von Neumann, 1935. He realized that this innocent looking operation has deep consequences. Can you guess it already? It's the next slide. All right. Now? No. Count the number of degrees of freedom. A vector, well, actually, that's my next slide. Oh, no, sorry. Before doing that, of course, matrices also, you could do the tensor product with them, right? It's nothing fancy. It's exactly the same thing. You take A11 and multiply by the whole matrix over there, put it as the first guy, right? Then they take A12, multiply by the whole matrix, put it over there, right? So if I want to write this schematically, in the same notation here, schematically it looks like this. If you have a matrix A11, A12, A21, tensoring by some A. Now this is some matrix, right? This is a giant matrix. B. This is a giant matrix. The result would look like copy this giant matrix here, multiplied by A11. Copy this giant matrix here, multiplied by A12. Similarly, A21 times B. This is what tensor product is. Notice there is an order. That's important, right? When you have the tensor, and what does tensor product describe? It describes what you would think it describes. If I have particle 1 and particle 2, and I want to perform an operation A on particle 1 and operation B on particle 2, and the states are alpha, tensor, beta, this is what it describes. Because now my alpha, tensor, beta is a larger vector. If I want to represent an operation on it, I should have a larger matrix. Any questions about the operation? All right, so here is the magic. Oh no, actually, I'm gonna let me just first say formally what the postulate of composite systems is. It says the state space of a composite physical system, this is postulate 4 of quantum mechanics, is the tensor product of the state space of the components. If psi I is the state of component I, the joint state is psi 1 tensor psi 2 tensor all the way to psi n, and it belongs to the Hilbert space H1 tensor H2 all the way to tensor Hn. Right? This is a composite system postulate. I guess postulate 4 the rubber count. Yeah.
This formalism, like, was it developed side by side with the rest of the quantum mechanics after Dirac?
Oh no, von Neumann is like before. Well, this is 1935. Dirac is also 1920s, 1930s. So von Neumann was a mathematician. Tensor product and Dirac sums, just basic operations in linear algebras. They've been known forever. The difference between physicists at the time and someone like von Neumann was that von Neumann had a profound understanding of linear algebra and like all this formulation, whereas physicists were building this very pragmatic. They had to explain the things, and they were just inventing things. I was telling you a couple lectures ago that Heisenberg didn't even know much about matrices. He knew about matrices, but not all that much. So if you read his papers, he was inventing things as he was going along. As usual, a lot of times physicists come up with math as they develop things. But the genius of von Neumann, and actually entanglement is precisely was already seen as a shocking phenomenon, or the possibility for entanglement, in these abstract arguments that I had mentioned by Einstein, Podolsky, and Rosen. But what is 1935, same year, is actually when von Neumann noticed that mathematically this is in your face. It's just so obvious. You don't need. Well, yeah. So this is a postulate. All right, entangled states. So what is a pure state? Take a pure state of system A, or I'm calling it 1. I think in the rest of the lecture, I'm calling this A and this B. Doesn't matter, right? So if this is a pure state of a component A, psi 1, and psi 2 is a pure state of a component B, the result is a pure global state, right? How do you represent it? For example, let's do an example. Pick a psi 1, this vector, right? Which was the eigenvector of sigma x with eigenvalue half. This is the eigenvector sigma x with eigenvalue minus half. Tensor them, you obtain this 4-dimensional vector as a pure state of the global system. Good. Now comes the crazy thing. Not every pure global state is a tensor product of pure component, pure state components. There are vectors of the 4-dimensional Hilbert space that could not be written as a vector on 1, tensor vector on 2. These states are called entangled. Example, the 4 states I've written here. They're called Bell states. So it's a nice exercise for you guys to show that you cannot, by the way, the notation, in case I went through it fast, sometimes we write this to simplify our things this way, right? That's just a notation. For example, when I write 0, 0, I mean 0 tensor 0. Otherwise, there will be this tensor product operation all over. Right, let's pause here and think a little bit about what this says. Is the idea clear at least? Maybe you don't see why this could not be written as the tensor product of 2 vectors. I'm going to make it more clear on the next slide. So here's a definition. A pure state, for the purpose of this course, of a bipartite system is called entangled if it cannot be written as the tensor product of 2 pure states of its components. Pure state means vectors. A 4-dimensional vector in the Hilbert space is called entangled if it cannot be written as a 2-dimensional vector, tensor another 2-dimensional vector. Example, these vectors. These states, they're called entangled. Any questions? There's a lot going on that at first, as I said, these are innocent looking expressions with some very, very deep consequences. Let's see why this happens, okay? All right, let's see why this happens. Let's do a counting argument. A 2-dimensional complex vector, two-dimensional state of a qubit has 3 real variables. A second state of a qubit will have another 3 variables. So when you look at pure states of the system 1, tensor pure state of system 2, you have 6 real variables. Now take a vector in 4-dimensional complex Hilbert space. How many parameters do we have? We have 4 complex numbers, that is 8 real variables, minus 1, because there's a normalization, 7 variables. This vector has one extra variable than these guys. So there must be 4-dimensional vectors that could not be written in this form. Yeah. Well, if they were coming out as equal, then there was no clear, you would have been able to solve them, right? So the question is this: if you want to ask if there were no entangled states, you have to be able to solve a system of equations on the left is equal to right? Now, when you tensor them on the left, you're gonna get a vector with 6 variables. On the right, you have 7 variables. That immediately tells you that there's no way of solving for this set of equations. There's one free variable, which means that there must be states on the right-hand side that could not be written on the left-hand side. An example, I've already given you some of the examples. This state I've written on the board is entangled. Question?
Can you explain again how it's 7 variables on the right?
It's 4 complex numbers. How many real variables is that? 8, because every complex number has a real and imaginary part. Then these vectors are normalized. They should have norm 1, which means that the absolute value of alpha 1 squared plus absolute value of alpha 2 squared plus alpha 3 squared plus alpha 4 squared is equal to 1. That kills one variable, right? No? Good. Okay. Is there a question? Okay. It kills one variable, so we have 7. Yeah.
Saying that they're entangled if you can't get them from the components on the left.
Yeah.
Then how did we get it in the first place to know that we can't get it from the components on the left?
Very good. So it's postulates. How do we get it? We just followed our nose. The idea was this. We had a single particle. The rule of quantum mechanics was this, that there was a single particle. It had 2 classical options. We represented that by a 2-dimensional complex vector of unit norm when we went from classical physics to quantum physics. Now, when you classically put together 2 binary things, you get 4 options, right? It is natural to say the composite system, the quantum example of that, would be a 4-dimensional complex vector. That's why it's a postulate, right? That's why it's a postulate. It's not like given. How did we come up with quantum mechanics, right? Quantum mechanics, what were the postulates? I said that if you have a set of options classically possible that are like distinct option classically possible, d different options, you're going to represent pure states of that system using vectors of a d-dimensional complex Hilbert space, right? And that's all we're doing. As I said, this is very innocent looking, but it has this dramatic consequence. Even Einstein and those guys had not realized this simple way of thinking about it. Well, they had, I shouldn't say they hadn't realized, they had understood this in a physics example, but this makes it very, very manifest. Are there any other questions? This is a good moment to, oh, sorry. This is a slide I will have. So, said differently, states of 2-particle systems have something more, have 2-particle systems have states that have more than just their components. There's in quantum mechanics, by putting systems together, there is room for some new degrees of freedom that we refer to as entanglement. A composite system is more than its pieces due to entanglement. So there are these 4 vectors that we call Bell states, and if you ever look at qubit systems, Bell states, they're all entangled, they are orthogonal, and they play an important role in entanglement theory, we usually write them using this notation. Hopefully that is x and y are integers, right? 0, 0 plus 1, 1, 0, 0 minus 1, 1, 0, 0, 0, 1 plus 1, 0, 0, 1 minus 1, 0. Yeah.
The null states, so they're just a sum of two products.
Yeah.
Right. Could you just add like, as many combinations, and is that still valid, or is that the formula?
Yeah. It becomes another vector, right? The question is, well, you only have, it's a 4-dimensional vector space, right? We're counting, it's a 4-dimensional complex vector space, right? So you have 7 variables, and here the point is that these are orthogonal. These are orthogonal entangled states. We're gonna come to this later. They're not just entangled, they're maximally entangled. They have taken this entanglement property to the extreme. That's why we talked about them.
Is there a bar with that line?
Yes. Oh, sorry, I did not explain that. So this is a shorthand formula for reproducing those 4 numbers up there. X and Y's are zeros and ones, and bar means not. 0 goes to 1, 1 goes to 0. This is just a shorthand notation. Just plug in x equals 0, y equals 0. You're gonna read that. You're gonna get 0, 0 plus minus 1 to the power of 0, which is 1, 1, 0 bar, which is 1. Thanks for asking. Yeah, that's notation at next one. All right. Yeah.
Why do you write it that way?
It's a notation that people use. Here it seems obnoxious, but when you talk about many of these guys, then the dimensionality of the Hilbert space grows. So the expressions that are formed at the top might become hard to keep track of. There are many terms. So sometimes compact notations are useful. It's just compact notation. It doesn't have any physics in it. I actually never use that notation. I had to look it up. Let's just leave it at that. All right. So what did we see? We saw that when we put together 2 qubits, right? There were 6 degrees of freedom that were sort of easily explainable, and then there was 1 degree of freedom that was extra. The problem is, as you go to larger and larger dimensional Hilbert spaces, almost all states are entangled. Almost all states, the vast majority of states of the Hilbert space are all these weird states. Just let's do an example. So let's take it pure, instead of qubit by qubit, let's do qubit by qubit, right? So a qubit is a vector of complex number C1 to CD with 1 normalization condition. That is 2 times D minus 1 real variables, right? When you tensor 2 of those pure states, you get a vector with 2 times 2D minus 1 variables. But when you look at the pure state of the composite system, it's a vector that lives in a D squared dimensional Hilbert space. Alpha 1 to alpha D squared. This has 2 times D squared minus 1 variable, right? The number of variables on the right-hand side of an analogy explodes. Take D to be 100, right? The first line is 2 times 199, right? Down here you have 2 times 10,000 minus 1, right? Now, just run the analogy for a second. You have an Avogadro number of atoms, right? 10 to the power of some absurd number, right? If you take an absurdly large number to the power of 2, it means that you're screwed. The vast majority of these states are entangled. Yeah.
But if they're interacting with these blocks, that destroys them.
No. We at the moment we're describing the state space, so we're not describing entanglement or interactions or anything. But that is a definite no. So I know what you're talking about, and just, yeah, let's hold on that. Any questions? All right. So, how many of you guys have heard of quantum gates? Okay, good. So at least some of you would use this. I could use this language. I have a couple of slides to introduce a language, or we could avoid it. So if you find it helpful, I can introduce a language. It's very, very helpful for doing calculations. So actually, you guys are truly the generation of quantum logic and quantum gates, not even my generation. But yeah. All right. So what am I gonna do? Now I'm gonna wear my experimentals hat, which doesn't fit me at all. And pretend we're gonna create entangled pairs, bell pairs, right? In an experiment. Good. And we want to know how to create an entangled pair, just experimentally.
You're not allowed to do this.
What's that? Yeah, no. No, there might be experimentals out there that might be the of how I just future of the discussion. Anyway, so we're going to introduce an analogy with classical quantum, computer science, where we talk about zeros and ones, and you apply gates to them. We're going to introduce a bunch of quantum gates, right? So this is just like a line means a qubit, right? Classically would be a bit, 0 or 1. Here you have a superposition of them, right? A line classically was this, 0 or 1 was the input, and then you do something. For example, you do a NOT gate, which sends 0 to 1, 1 to 0. Right? If you do a NOT gate to a quantum state, now what comes in is alpha 0 plus beta 1. What it does is it sends ket 0 to ket 1 and ket 1 to ket 0. So this is what you get. Do you recognize this gate? This is sigma x. It's the Pauli x. Right? That's something classical. Now the Z gate does something deeply quantum. It sends 0 to 0, but it multiplies the ket 1 with a minus sign. That's only sensible if you have superpositions. Classically, there's no analog of that. Right? Now, there is the Hadamard gate. What it does is that it rotates the sigma z basis to the sigma x basis, right? It sends 0 to 0 plus 1 over square root 2 and 1 to 0 minus 1 over square root 2. It's just a rotation. It applies a rotation. And it's that matrix. So these are single qubit gates, quantum gates. The NOT was classical already, sigma x was already classical, but Z gate and Hadamard. Are there any questions about that? I just need one extra gate, which is also classical, and then I'm good. I don't need any more. I could introduce sigma y, but I don't need to. Why? It's actually multiplication as well. If you multiply sigma x and sigma y, you're going to get something that, sigma x and sigma z, you're going to get something that's like sigma y. But commutator is literally. Good. I'm going to introduce, inspired by classical computation, an operation called C0. It's an operation on 2 bits. It says, so there is a control bit on the top where we put the black dot. So this is called the control bit. Nothing happens to the control bit. If the control bit is 0, this bit is unchanged. If the control bit is 1, you NOT the second bit. So 0, 0 goes to 0, 0, 0, 1 goes to 1, 0, because if this is 0, nothing happens. This part of the gate is identity.
Should I put a 0, 0?
Oh, sorry, that's a typo. Thank you. Yeah, that is, thank you. Yeah. But if this is 1, again, nothing happens to the control qubit, but the other guy is flipped. 0, the second one goes to 1 and 1 goes to 0. This is C naught. Sometimes it's called C as a controlled naught. But naught is sigma x. We could call it controlled sigma x as well if you want. And by analogy, you can imagine doing controlled your favorite single qubit gate. Right? But these are all the gates I need. If there was if I introduce one extra gate, I would introduce all the gates you ever need to know. But we're not gonna do that. I don't need it.
Is that a 4 by 4 matrix?
Yes. Good. Oh, actually, wait a second. Whoops, I totally forgot to include how to create bell pairs. Let's do that. I totally forgot this slide. All right. Had them on first. Okay. So, bring in 2 gates, right? Bring in 2 qubits. We're gonna do a C naught and a Hadamard here. Actually, now this is an opportunity for me to give you a homework problem. Show that this prepares a bell state. How would you do that? First, take as the input some sign off. A pure state of the tensor. For example, 0, tensor 0. We write 0, 0. Good? Then write the state here. What is psi 1? So what is this vector? This vector is 1, 0, 0, 0. Psi 1 is the gate C naught, that 4 by 4 matrix, applied to this vector. Actually, that already tells me that no, actually, that's not. Yeah, so this is going to be 0, 0, 0, 0. And it remains the same. Then apply a Hadamard to the first state, psi 2. You get this state. Right? This state is not going to be entangled. However, if I put in 0 plus 1 over square root 2 here, and 0 minus 1 over square root 2 here, show that what comes out is a bell pair. So how do you get bell pairs? Using C naught. From bell pairs are entangled. The input is an unentangled state. This circuit, which is C naught followed by Hadamard, creates entanglement. I'm going to pause and ask for questions. Am I missing another Hadamard? Well, I'm not missing another Hadamard, but you figured this out. It's pretty easy. Multiplication. I think I'm missing another Hadamard. I need a Hadamard, C naught Hadamard, but I'll check that. But are the rules of the game clear? What we're doing, what these diagrams, these quantum circuits represent? Any questions? Okay. All right, let me tell you in words what I'm gonna do in the remainder of this lecture. So we have half an hour left. First, so for now we've seen there are these entangled states. Now I'm gonna tell you some of their weird properties. The next lecture and the next lecture, the lecture after that is going to be even weirder and weirder properties of it. By now I've defined them. Today I'm gonna talk about two things. First, one of the weird properties of these entangled states that has to do with the reduced density matrix. Okay. Second, I'm going to show how these entangled states give you quantum teleportation. I'm just going to tell you how quantum teleportation is done, and it's insane. Honestly, the first time you hear it is insane. What is quantum teleportation? What is teleportation? You do something here, and your thing disappears and pops up somewhere else. This happens without you physically transporting it. If I have a classical bit, right? How do I transfer it to you? I pick up my phone. Well, this is old school. I pick up my phone, right? And then the signal is transmitted physically, either through a wire or through some electromagnetic wave. That is some medium is literally carrying your thing. You encode your 0 and 1 in some magnetic state or something, or some photon polarization. That thing is literally moving to the next person. Teleportation is a setup where, at least in sci-fi, nothing is transported. I have a state here, I do something here, you do something there, over there, some magic, and then your state disappears here and pops up over there. This is what we're gonna do. But let's be clear what happens. And now what we want to do is transfer a quantum state. I can encode the quantum state in the state of some photon or something, right? Quantum or qubit, like the way that Alex Ma does it, for example. You could take that sample, physically move it to Vienna, give it to Anton. What we're gonna do is we're gonna transfer a quantum state without physically moving it, right? Well, the state is Alice and Bob, me and my friend. We have I have a state side that I want to send it to them. I do something here, they do something there, and this state disappears and pops up over there. Good. There's a caveat. In sci-fi, what happens is that you do something here, they do something over there, and then the state pops up over there. That violates causality, right? We could be infinitely apart, right? The person could be not infinitely. There could be in the Andromeda galaxy, and I could be here. If I could transfer my quantum state to them, I've violated Einstein's relativity. This was Einstein's objection. This was literally Einstein's objection. He said that if you could do this, you can transfer your information really, really far away instantly, and that violates the laws of nature. Turns out that quantum teleportation has an extra subtlety to it. You do something here, right? Instantly, something happens over there, but the information that person doesn't have it. I have to pick up my old school telephone, tell them give them some classical communication. Based on what I tell them, I give them a secret classical code. Based on that, they do a measurement and voila, state pops up. Before that, before I tell them, do this measurement, I have to tell them what they do. And I cannot tell this in advance. So quantum teleportation teleports quantum information, but you have to classically communicate something to them. This is how Einstein's relativity is respected. We'll get there. Okay, so let's go step by step. By the way, be prepared for a lot of, fortunately or unfortunately, philosophical consequences. We're going to go through that, not in this lecture, but the next lecture we're going to talk about EPR pairs, and wacky stuff are going to happen, but we'll see. Okay, so I told you how to get a composite state. I said, if you have a pure state of particle A and a pure state, a vector of particle B, you tensor them and you get a vector of the composite system. Now, if you have this composite vector and somebody asks you, what is the state of system A? You say psi. Somebody asks you what's the state of system B, you say phi. Now, take one of these entangled states, this guy. It is a pure state, it's a vector of a state that Alice and we share. But you ask, what is my state? Or what is Alice's state? Well, what's the answer to that? It cannot be written as something tensor something. So what is that state?
Depends on the other person's state.
No, we are sharing a pure state. We are sharing this Bell state together. And we do know this is our state. We know everything about the state jointly. But the question is, what's their state? We already know because it's entangled, it cannot be pure, it cannot be a vector. Right? Recall when we were talking formula in quantum mechanics, I said we have density matrices that are not pure, they're mixed. At the time I motivated this as some sort of classical uncertainty. I want an ensemble. Here it turns out that the state of Alice and Bob or Alice and me when we share this state is a density matrix that is mixed. This should be shocking because in classical physics, classical mixture of probabilities comes through coarse graining. There is I have crappy measurements, and because of that, I have classical uncertainty. So I took a bunch of states, psi i's, and I said, well, I don't really know which one it is. I'm just going to add them with some probability distribution. Here, what is happening is that you could know anything that's there to know, but still your state is a mixed density matrix. That is why we had to generalize the postulates of quantum mechanics to include density matrices in them. Any questions about this? So we're going to go through this slowly. First thing first, I'm going to define for you how to calculate the reduced density matrix when the state is this. Anyone has a guess? You trace one of them. You trace out one of them. That because you trace out only one of them, that's called partial trace. All right. So we define a partial trace. Here's a density matrix of the bipartite system, where density matrix of A is trace of B applied to this. What is it? So I'm just going to tell you what the operation is at the level of linear algebra. Here is a general operator in the Hilbert space of A tensor B. Ket bra C1, C2, tensor ket bra D1, D2. Trace, partial trace over B just acts only on these guys. So this guy comes out. Now you take the trace of these guys. The trace of ket bra D1, D2, which is bracket D2, D1. Right? It just flips them, guys. So if I did this to pure state, tensor pure state, what do I get? I have my reduced density matrix of A would be trace of B, psi A, tensor phi B, ket bra phi. Trace of B only acts on this guy. It would be trace of phi, which turns the ket bra into bracket. Phi is 1. I get this. Recall that this is a pure state. So this operation is consistent with what we knew. All now I need to do is to calculate the reduced density matrix for the entangled state. Everyone follows this slide? So when we put together pure state to get composite systems, we did tensor product. we're inverting that. Inverting that is like taking part trace of one of them. If you have a tripartite system and you want to know, say, A, B, C, and you want to know the state of C, you would perform a partial trace over A and B, right? Logically, you can generalize. Good. Okay, so here's a bell pair state, entangled state. First, I calculate this rho AB. Its rho AB is this guy. This is rho AB. Why is that? Because, oh my God, it doesn't write. So this was what my notation was beta 0, 0. And this is, why is my? So this is just beta 0, 0 ket, beta 0, 0 bra. Remember that density matrices for pure states were just ket bras. So this is what it is. I expand it, I get this expression. 0, 0, 0, 0. There's a half that I bring out. 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. So when I do a partial trace, what happens to the first term? The second guys flip. This becomes, let me do it on the board so that you see it. Maybe that is too quick. So I'm going to calculate trace B of 0, 0, 0, 0. We take these two guys and turn them into a bracket. So these two guys come out. This becomes trace of B of 0, 0, which is 0, 0, 0, 0. This is 1. This is 0, 0. That's the first term. What happens to the second term? The second term is 1, 1 here. So this is 0, 1, 0, 1, 0, 1, 1, 1, 0, which is 0. So there is no term here. The second term drops out. Similarly, the third term drops out. The fourth term will give you a 1, 1. What do you obtain? You get the density matrix, which is maximal and mixed. With probability half is up, probability half is down. This is the best description of the quantum system. First bizarre consequence of entanglement is that for entangled states, even though you and Alice might know exactly all that there is to know, but each of you individually is missing information. Actually, we'll define entropy later. Alice and I, we share a qubit pair, an EPR pair. Together, we know everything that's there to know. I know nothing, she knows nothing. That is the consequence of it. Because when I have this half up, half down, I mean, I know nothing, it's just totally random. It looks totally random to her, it looks totally random to me, but together we know everything there is to know. Yeah.
That's the last line. Product times, bracket of 1, 0. Does that make the whole thing 0?
Yeah, this term vanishes. This term vanishes, yes. So this was the second term in the sum. Yeah, the 4 terms. The second term and the third term, this happens to them, so they vanish. I've drawn the black arrows. Those are the only surviving terms. So it's possible, in entangled states, as I said, like I repeat it, you and your friend you know everything that there is to know about the state, but individually, either of you knows nothing. This is a weird phenomenon of entanglement. We'll talk about what it means to know nothing. What is information, quantum information? We're going to quantify that and make this statement, which sounds emotional, more rigorous. So let me repeat. In quantum mechanics, we get ensembles without coarse graining. We're doing the best we can. We know everything about this global state. multipartite bipartite state. Nonetheless, you must use probability distributions and averages to make sense of things. This is the only way of, when you talk about reduced density matrices, that's the only way there is no coarse graining. There is no statement about, oh, somebody did poor measurements or something. We're not even talking about incompatible observables. We're just given a state, and we're asking how much we know about this and who knows what. Density matrices are inevitable. It's not in statistical quantum mechanics that you have to introduce probabilities. It's in quantum mechanics that you have to introduce. You don't need to introduce statistics. The statistics is in your face. You have no choice but using them. Yeah, I invite you to think about this. We'll talk a lot about this. How is it possible that you and your friend, either of you knows nothing, but together you know everything? Any questions? All right. I'm gonna pause because it gets weirder and weirder. In the remaining 15 minutes, I'm just gonna go over quantum teleportation, the protocol. Good, but it's a good moment to pause and ask for questions. Now you know all the mathematics you need to do calculations. You need a tensor product and partial trace, and that's all that you do. Yeah.
Is it preferable that that's actually?
Okay, we'll talk about that. Yeah, if you used states that were not, they exaggerate the phenomenon. If you use states that are non-maximally mixed, then you end up in these situations that you know a little bit, your friend knows a little bit, but the sum of what you know is less than the whole thing. This maximal entangled states exaggerated. You know nothing. This is the extreme case. The other person knows nothing, but together you know everything. There's actually a sense in which you could know, in quantum mechanics, you could know less than nothing, you could know a negative amount. There's a very famous, beautiful paper that was published by Popescu and friends. And the title of it is The Scientists Who Know Less Than Nothing. That's about conditional entropy, blah, blah, blah. There's a lot that's going on with quantum states. There's a lot of weird phenomena. All right, so quantum teleportation. Let me pause a little bit more. Do ask questions if something comes up. This is the thing that really I fell in love with back then as a high school student or undergrad. I didn't understand when I was a high school student, but like as an undergrad. And I didn't know one day in my research, which went down the path of quantum gravity, this would be my everyday calculations or things that I use. But it turned out that they're related. I'll tell you later a little bit if there's interest. Okay, very good. So what is it? I'm describing teleportation. In this example, Alice, my friend, has a qubit in state psi. Let me write it. Alice has a qubit in state psi. And I repeat, this one has been experimentally demonstrated, like at all, I said at the beginning of the lecture, at like ridiculous scales. So Alice, my friend, has a state psi that wants to transfer. Before we start doing anything, the condition is that we have already shared an EBR pair, sorry, a bell pair. So these two lines means that, so Alice holds these two qubits and Bob or me have, let me just use the word Bob. Bob has only one qubit. Well, how does the protocol proceed? Alice has a psi and half of a bell pair, and Bob has a half of a bell pair. Alice does a bunch of things to her qubits. Her stuff just kind of are destroyed. And all of a sudden, psi pops up here. That's the idea. So the outcome here is going to be psi. And this is what they do. Okay? But you need to share an EPR pair. Sorry, when I say EPR pair, bell pair. It's also called an EPR pair. So what is the initial state? Is ket psi tensor this. This is psi naught. Good? Everybody's with me? So how does the protocol proceed? Let me just say it in words. So I'm describing what Alice does. First, so Alice has 2 qubits in her hands. One of them she wants to transfer the state of to me, but she's not gonna send the qubit to anybody. First, she's gonna do a controlled knot on her 2 qubits. Control being the state of interest. So first, nothing really happens first, state of interest. It's a controlled knot. Something happens to the bell pair we share. Then she applies a Hadamard, a rotation to her state, right? Everyone's with me? So far, it's pretty straightforward, and we're all the way down to here. Nothing has happened with Bob. Now, Alice has 2 qubits. She measures them in the Z basis, both of them. So the readout is, there are 4 possibilities. Remember the collapse of the wave function. There are 4 possibilities. Either 0, 0, 0, 1, 1, 0, and 0, 1, 1. What she does is that she picks up her phone, old school phone, because this was done in 1997, and calls Bob and says, I saw 0, 1. Based on what she says, Bob performs a gate, voila, pops up psi. If she saw 0, 0, Bob has psi, doesn't need to do anything. If she saw 0, 1, Bob applies Z, sigma Z, not. If she saw 1, 0, Bob applies X. If she saw 1, 1, Bob applies XZ. So in the next slide, which is my last slide, I'm going to show you that this is true. This happens. But is the idea clear, right? Yeah.
Is psi 4 the same as the initial psi?
Yes, we're going to show that it's psi 4 is the initial psi. Is the idea clear? Now, what is really weird, here is this, again, I invite you to think about it. There is a possibility, there is some non-zero possibility, like a certain number of times, what comes up is 0, 0. So Bob already has the state psi in his hand, but he just doesn't know it. In a sense, the quantum state has already teleported, but it's useless if you don't know it, right? You might have the right state, but you don't know whether you have the right state. So yeah, think about these things. And you know, something that's really, just 1 second, something that's really funky, this blew my mind when it first was done experimentally. You could do this with systems like, with atoms, where the zeros and ones in creation annihilation operator. So your 0 is vacuum, and 1 is a single particle created. So literally the particle disappears here, and it pops up over there. The particle pops up over there. Yeah.
Is this like doing is this like, so you were saying that if it's 0, 0, you do nothing, you already have the state, but you don't know, Bob doesn't know he has the state.
Yeah.
Unless he knows what the measurement is on the other side.
Yeah.
So is this kind of like saying, we have like axes, so if we have some axis of what we're looking at the state from some point of view.
Yeah.
And those axes are with respect to the mixed states, then you don't have to do anything, you don't have to rotate to actually see the state. But you don't know what axis, like angle you're at, unless you know what the other one is. And so then, once you know the other one, you measure to then rotate to 0, 0 to get the state, to know that you're looking at it almost from like a pure state, you're looking at it from like a pure state, but you've done like a change of basis almost.
Yeah, so okay.
Using the mixed state.
I see what you're, as I said, this is not straightforward. I'm gonna go over on the next slide, what's gonna help you, as I've said many times, you guys are physicists. you should write expressions and stare at them for a very long time. That's your job. And think about what the equations say. So on the next slide, I'm literally going to follow all the things that we've learned together and show that the psi comes out. And I invite you to think about every line of that.
Size of 1 qubit state?
Yeah, in this example. It doesn't have to, but yeah.
Oh, okay. Yeah, I was gonna ask what's the advantage if you have to do classical communication?
Very, very good. Sorry. No, but a classical communications is 0 or 1. It's a bit. What is a qubit? It's 3 real variables. If I might describe to you 3 real variables, that's a lot of information. I have to give you 3 real numbers. Whereas whether I say 0 or 1, I can have a missed call. I can do missed calls, right? That's easy to transfer. Whereas I can't transfer 3 real numbers that way. Okay. Any other questions? All right, so let's do the calculation together. I wish I could have both of the slides together. Let me try it. Yeah, okay. So let me just say this. Okay. Psi 0 is the initial state. I'm just going to use it here. Psi, which is this state, tensor a bell pair. That's psi 0. Okay? Everybody's with me? I'm going to write the state first after a C naught that Alice does, then after Hadamard that Alice does, and then finally after the measurement applying this. So that's my psi 1, psi 2, and I have to show you psi 4. I jump to psi 4. Okay? All right, so let's do that. So this is the initial state. This is my psi. I'm going to expand it. Alpha 0, the state, I've taken square root 2 out, 1 over square root 2 out. Beta 1, this is the state. That's my initial state. First operation is C naught on the first 2 qubits. So alpha 0, the first qubit, which is the control qubit, is 0. So nothing happens. It's controlled not. Second part, this is 1. Therefore, the second qubit is flipped. Right? Are you with me on psi 1? I apply the C naught to the, and nothing happens to third, right? I apply the C naught, controlled being first qubit, second qubit where the action happens to being the second. And the next step is the last step, actually. Then Alice applies a Hadamard to her qubit. So first qubit, 0 goes to 0 plus 1, 1 goes to 0 minus 1. That's all that has happened. Good. So you have this mess of an expression. Everybody's with me? Now just expand this term by term. Subtract and reorganize, you get this expression. That's just like addition and subtractions. Let's interpret this. This says the state of the first 2 qubits is 0, 0 tensor psi plus 0, 1 tensor x psi plus 1, 0 tensor z psi plus 1, 1 times zx psi. Now the measurement is straightforward. If Alice measures the first 2 qubits and finds 0, 0, this is the state of Bob. Just as projected to this. If she finds 0, 1, this is the state of Bob. Now, how do you undo x? You apply x again, because x squared is identity. If she finds 1, 0, this is the state of Bob, z psi. How do you undo z? You apply z. Finally, if she finds 1, 1, you get zx psi. You do apply xz, it will undo it. Right? That's it. This is teleportation for you. Then after the measurement, Bob applies those operations, and his state is psi. So psi 4 is psi. We did not violate causality because we did not send information faster than the speed of light. We had to call them on the phone line. However, we did something nuts. By giving a 2-digit number, we transferred a 3 real variable worth of information. We teleported. This is not sci-fi, this is reality. As a matter of fact, this is a very, very efficient way of sending quantum information rather than an actual physical channel. What happened? This was not free, this operation. You can't teleport like arbitrarily. There's a cost to it. What is the cost? Can you see what the cost is? You used entanglement. You started with an EPR pair, and after your protocol, your EPR pair is your bell pair is destroyed. So it's like the cost. You need to have, if you want to do teleportation, a certain number of qubits. You have to have an equivalent amount of qubits, bell pairs in your bank account. You're spending it. There's no free lunch, right? However, you do this wacky thing. Right? Okay. This is not going to end here. This is the end of this lecture. And I'm going to answer questions, but we're going to come back to bell pairs and talk a lot about various aspects of it. At first, we're going to talk about EPR, paradox or confusion. The EPR confusion is going to get resolved and you're going to feel okay with it for a while until we talk about Bell's theorem. That is when you're hit like really hard. That is really, really weird. Okay? All right. Are there any questions? Yeah.
At the start of the protocol, with Bob and Alice, they prepare the Bell state.
Yeah.
In their own labs.
They must somehow create that. You know, Bob and Alice, at the beginning of the grad school, they had access to a good lab and they created like all sorts of bell pairs and they shared them half and then they walked away. Long time later, they're using that resource to do this. So this is precise terminology. Entangled pairs are a resource that you spend, right? It's a cost, it's literally. So if you have prepared EPR, bell pairs, entangled, if you're entangled with someone, you have a resource that you could use to teleport information. Another thing that's really funny is that if you're entangled with someone, in a sense, it's horrible for security. Because they could be teleporting your information elsewhere and you might not know about it. So in quantum cryptography, if you have some information you want to keep safe from the rest of the universe, your goal is to cut off entanglement. You want to kill entanglement in cryptography. That's why Swiss banks use this kind of stuff. One of the major applications of this kind of business is quantum cryptography, because people want to make sure that, I'm oversimplifying here, but not by much. Not by much. The first step in stealing something from someone, quantum mechanical, without going to their house, is long time ago, before they buy the house, put in some EPR pairs, bell pairs. All right, thank you so much.
Someone had like happened to have the same half of the bell pair as Bob and happened to